Okay, all right, so I'm recording now, okay. All right, so I definitely want to review this first question in this packet. So this is our going over the new material on chapter 9, MO theory. This is the very last section and the most advanced bonding theory that we learned about in chapter 9. Where we see, Lewis structures can't 100% cover all structures that we want to draw. There's some limitations to Lewis structures, but what we learned here is that MO theory combines to those advanced theories of valence bond theory and the idea that electrons are actually waves together into one theory. So this is molecular orbital theory to correctly describe the bonding in molecules. So here I have a bunch of different pictures. These are our molecular orbitals. So we form molecular orbitals by combining two atomic orbitals. Atomic orbitals can combine their waves in two different ways, either constructively or destructively. So when we have constructive addition of waves, we get bonding orbitals. When they're destructive, we get anti-bonding orbitals. And that's these designations that you see right here. We got sigma, pi, sigma star, or pi star. So the stars mean anti-bonding. The sigma and pi are the same ideas that we talked about earlier with valence bond theory. So I have a bunch of different MOs here, and we should be able to, one, identify what type of MO is being depicted. So we should say sigma or pi star, etc. And we should be able to locate these MOs on this diagram, all right? So that is a learning objective from chapter 9. So when we look at one of these spaghetti diagrams, that's what I like to call them, what we want to focus on is the middle. Those are our MOs. These lines or boxes are where we can place electrons on our molecule. But on the sides here, these are our 2s and 2p interactions for two atoms combining their atomic orbitals, all right? So what you see here is that s orbitals, these two lines, these two atomic orbitals can combine two different ways. They can combine constructively or destructively where they're out of phase. So we see here two different combinations where this first combination is our bonding orbital and the second one is our anti-bonding orbital. So here we have sigma and sigma star. All right, so you should memorize what these molecular orbitals, the orderings are for these different diagrams. I'm going to just erase this real quick. So if we start from the bottom, when we put everything together, it goes sigma, sigma star, sigma, but between p orbitals, pi, pi star, sigma star. The points that I emphasize are that the anti-bonding orbitals are always higher in energy. See how these lines split? The ones that go higher in energy are always anti-bonding. The ones that are lower in energy are always bonding. If you have a single line, like a single box where we can place electrons, those are going to be our sigmas. Our pi interactions always come in pairs. So if we go to the very, very end where the supplemental information is, you'll see here two different diagrams. They're just slightly different in the orderings of the pi's and sigmas, but as long as you understand that pi's always come in pairs, the sigmas come singly, then you can recognize that pattern. We got sigma, sigma star, pi, sigma, pi star, sigma star for this one, and then this one is just a little bit different where the ordering of these two just swap. So it goes sigma, then pi, but then it's still pi star, sigma star, all right? So those are our orbitals, okay, or molecular orbitals. That is kind of the bare minimum you need to know about making these diagrams. So let's go back to our original question and actually place these orbitals where they belong. So here I did the first one for us. So A, here are those two black dots are our atoms. And so you kind of got to squint your eyes and think, what kind of bonding interaction is this? Is it bonding or anti-bonding? And then what were the original atomic orbitals used to create these? So in my mind, I see there's a lot of electron density between the two atoms. So to me, that signals this is a sigma bond, right? Sigma bonds have this head-on overlap, pi is side by side. And the two original atomic orbitals were s orbitals, because you can kind of see their spherical nature of how they overlap. So this is a sigma interaction between two s orbitals, right? So if we locate where that is on this diagram, I want you to notice there's actually two places there are sigma interactions, but which box is it? Is it the higher one or is it the lower one? It's the lower one, because this is the sigma interaction between the s orbitals. This sigma interaction is another head-on interaction, but it's between p orbitals, so it's not quite that one. So this a molecular orbital goes on the bottom here. All right, let's try to locate where is the sigma bond between p orbitals. Which one of these figures is that? That's going to be C. Yeah, exactly. So this is another sigma bond where it's head-on overlap, but if you squint your eyes, you can kind of see the original p orbitals that were used to create that. So you see a lot of similarities between A and C, but they're just made from different atomic orbitals. So there's another sigma, but it's between p orbitals. So that one goes here. All right, let's go through another one. All right, so let's do B. All right, so is this a bonding or anti-bonding orbital? Anti-bonding, what's the giveaway? It's this dotted line. That dotted line is called a node, and that basically is bond destroying, like an anti-bond. So adding electrons to an anti-bond destroys your bond or weakens it. So since we have that node there, I know that this is an anti-bonding orbital. So now we need to think, is this anti-bonding orbital created from head-on overlap or side-by-side overlap? This is side-by-side overlap. All right, so this is pi star. All right, so this one is going to go, it's going to be in one of those lines for pi star. All right, it's one of those. So this will actually occur in two different directions since we have two different orbitals there. All right, conversely, pi bonding is going to be E, because here we have, okay, similar, side-by-side overlap, but the electron density actually exists between the two atoms. We don't have a node that destroys the bond. So E is just regular pi bonding. Right, okay, what else? All right, so then we have D and F to look at. Here we have two anti-bonds. How do I know? Because there's nodes. So those nodes, again, bond destroying, they're always higher in energy than your respective bonding orbital. So D, what kind of anti-bond is this? Pi or sigma? Sigma, yeah, sigma star. What was the original atomic orbital? Is it a P or an S? It is a P, yes, very good. And then this last one is another sigma star, but it came from s orbitals. That was the original orbital it came from, right? So D goes where? Top, tippy top, tippy top. And then F goes at the top one within the s interactions. All right, so see how all that comes together? Okay, antibonds are always higher in energy than their respective bonding orbital. So this kind of covers valence bond theory a little bit, where we have to understand what kind of overlap's happening head-on or side-by-side, but then we need to consider the phasing as well. When we have out-of-phase combination of atomic orbitals, we get those antibonds to get those nodes, but when it's in-phasing overlap, we get bonding orbitals, all right? So that is the most advanced theory. Right, so then using these diagrams, actually this is probably the easy part. I think identifying where the MOs go in the diagram is probably the hardest. Filling them is actually quite straightforward. So according to MO theory, when we make a nitrogen, diatomic nitrogen, and produce a cation, so remove an electron, what happens? So with MO theory, using these diagrams, just remember, these are our MOs. This is where we're gonna place our electrons for our molecule, all right? So just like when we did Lewis structures, we want to count valence electrons, because right now what we're looking at are the molecular orbitals created by valence electrons. We're looking at the 2s and 2p interactions. So if this was like, draw a Lewis structure, we have two nitrogen atoms. How many valence electrons on nitrogen? 5. So 2 times 5, we place 10 electrons. all right? So you can think of it this way, okay, 5 electrons come from the atoms each, all right? So we start with 5 on this nitrogen, 5 on that nitrogen, but in the molecule, and that's what happens in the middle, in the molecule, here are MOs, we're just gonna rearrange those same 10 electrons, because 10 electrons come from the each nitrogen each. So we're gonna replace those 10 electrons in the center here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So notice how I still followed, Aufbau's principle, go from the bottom up. I still follow Hund's rule, maximizing spin for degenerate orbitals. And so now I'm done. So I just rearranged those 10 electrons. I didn't have to put the electrons on the side here. I'm trying to show you where they came from. Sometimes I also draw lines because I'm lazy and I don't want to draw the arrows. Okay, so let's actually answer the actual question. Right now, I've drawn diatomic nitrogen, neutral, but here I want to produce the cation. So I got to remove an electron. So to make the cation, always start with the neutral thing and then just add electrons or remove electrons as necessary. So here, to make the N2 plus cation, I'm literally going to just remove, boom, 1 electron. There you go. So we want to know, how does that affect things like bond order, bond length? So let me just put that electron back, and we have to calculate bond order, right? So to calculate bond order using MO theory, we want to count the number of bonding electrons, subtract the number of anti-bonding electrons, divide by 2, right? So that means we have to, again, memorize the ordering of those molecular orbitals. It goes sigma, let's pick a different color, let's do green. Sigma, sigma star, pi, sigma. So when we look at this diagram, there's a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons in bonding orbitals, minus 2 electrons in anti-bonding orbitals divided by 2. Bond order of regular neutral diatomic nitrogen is 3, right? So we want to know, how does the bond order change? So let's make the cation, meaning we remove an electron, right? We remove an electron. But let's, even without, so we remove the electron and we can just recalculate bond order and make a comparison. But let's just think about this logically. If I remove an electron from a bonding orbital, or here, if I say this, what if I add an electron to a bonding orbital? What will I do to the bond? Strengthen it or weaken it? Strengthen it if I add electrons to bonding orbitals. Look at this equation, all right? If you add electrons to bonding orbitals, then bond order goes up. But what if I remove electrons from bonding orbitals? How do I affect the bond? I weaken it. Yeah, just mathematically, this bond order will go down. What if I add electrons to anti-bonding orbitals? You do what to the bond? Weaken it. Yes, very good. And then finally, what if you remove electrons from anti-bonding bonds? Then you also strengthen the bond in that case, because you think an anti-bond is a bond-destroying orbital. So if you remove electrons from it, then you strengthen the bond. So even without calculating it, all right, and when we make our cation, we remove what kind of electron? A bonding electron. So what do we do to the bond? We are weakening it here. So here bond order is going down. You can calculate it. This has a bond order of what, 2.5? Is that right? Yeah, 2.5. Good. But I want you to think about it logically as well. So bond order decreases. It goes from 3 to 2.5. What effect does that have on length? It actually lengthens because its bond order is going down, right? What does that do to bond enthalpy? Enthalpy just means strength. So how does our bond change? We are weakening it because bond order is going down. And then finally, what about magnetism? Here, diamagnetic just means everything is paired. Paramagnetic means you have at least one unpaired electron. And so here we see the cation is paramagnetic, right? But the neutral diatomic nitrogen is diamagnetic. Everything was paired before we removed that electron. All right, so that's how you use the diagram. You can do this for any substance when given this diagram. You just need to know how many electrons you place and what kind of MOs you're placing them in. All right? Oh, so let's do another one. Let's do this one a little faster. So we're doing the same thing, but here we're making diatomic carbon and making an anion. All right, so let's go through this quickly. So 2 carbons, so how many electrons? 2 times 4, 8 electrons. So I'm just going to go ahead and put those in the middle here. 1, 2, 3, 4, 5, 6, 7, 8. All right, so tell me what, so this is for just regular C2. What is the bond order for this? Can you calculate that? It is what, 2? Is it 2, bond order of 2? Yep. So I can go ahead and label this sigma, sigma star, pi, sigma, sigma star, pi star, sigma star. My hand wrote the right thing, my mouth said the wrong thing. Okay, so there's the bond order. Right now, is this substance diamagnetic or paramagnetic? Right now it's diamagnetic, but as soon as I make, what are we making? The anion. How do we make an anion? We add an electron. So you add it in the next available spot. Which spot is that? It is the sigma. All right, so now the anion is paramagnetic because now we have an unpaired electron. What did we do to the bond order? We increased it. What did we do to the length? We shortened it, and how did we change the strength? We made it stronger because bond order went up. All right, perfect. All right, do we feel good about that? Yes, MO. All right, so, okay, so that's all of chapter 9, okay? Using these diagrams, it really is just, actually MO theory is the 100% correct analysis of Lewis structures. Really what you're doing here is solving the Schrodinger equation for these molecules. All right. Okay, and usually we have supercomputers do that. Okay, so this is chapter 10. Gases, oh, there's a question here. Does MO order of pi's and sigma always look the same every time? No. So the question here is the ordering the same every time? No. It depends on what substance we're looking at. So if you're working with these things, the ordering of these two goes pi then sigma. If you're working with OF or diatomic neon, which is uncommon, it goes sigma pi, right? So those are the ones you want to use. Do diagrams only work for the diatomic? Yes, that's correct, all right? You will not be asked something that's not on the diagram. If it's not one of these diagrams, we have to give it to you because we do not expect you to solve the Schrodinger equation on the exam yourself. All right, so gases, I don't really want to spend too much time on this, all right? I want to basically tell you the bare minimum you need to know. This first question, we are changing a sample in different conditions, so we're not changing the amount of matter we're working with. So this equation, number 4, uses the combined gasol, P1, V1, T1 equals P2, V2, T2, all right? When you use this equation, pressure and volume, those units just have to match. It doesn't matter what it is. They can be ATM, it can be torr, they just have to match. But temperature must be in Kelvin, okay? So here in this question, here is V1, this is T1, this is P1. I give you a new temperature, so here's T2, and then here is P2, go ahead and solve for V2. So again, make sure that your units match. Here, you'll have to change the unit of temperatures to Kelvin, and you need to make sure the pressures match. So one's in ATM, one's in torr, so you just have to make a match somehow. If there is one pressure conversion you need to know, 1 atmosphere equals 760 torr, or millimeters of mercury. That will get you far enough, all right? So do know that 760 number, all right? So note here, we're taking a sample and just changing its conditions. So yeah, we're gonna solve for V2 in this case. V2 will be in the unit of liters because volume is in liters, right? Okay, so let's keep going. So in this one, Number 5, here, gases are sold in large cylinders. What pressure in atmospheres is exerted by 2 kilograms of oxygen stored at this temperature and this volume, all right? So I'm asking, what is pressure? So since I'm giving you an amount of gas, we don't want to use the combined gas law. We actually want to use the ideal gas law, PV equals nRT, all right? Because we want to solve for pressure. That's what the question's asking for. I give you volume, I give you temperature, R is a constant. So you might be wondering, how do I get N? How do I get the mole amount of stuff there? Oh, it's given by how much oxygen is present in kilograms, all right? So this is pulling back ideas from chapter 3 that we can determine mole amounts of substance if I give you gram amounts of substances. So here I'm telling you, oh, you have 2.5 kilograms of oxygen. When you and I interact with oxygen on Earth, what's the formula, the chemical formula of that? O2, yeah, so it's not 2.5 kilograms of O, all right? You and I, we don't breathe O, atom, we breathe O2, the molecule. But that's important because we have to use, in order to convert grams to moles, we need molar mass, right? So if you use O, you'll get the wrong molar mass. So that's why I point that out. So let's convert this into grams first, and then convert this into moles. So 32.0 grams is 1 mole of O2. Whatever this number is, moles of O2, this is your N value that then goes into Pivnert, all right? So that's the strategy there, that you will get that N value from the gram amount of substance that you have, all right, from your gas. All right, I don't feel like doing the actual work. Okay, unless you want me to do the work, no? No, okay, let's keep going. All right, let's do this one. This is the idea of partial pressures, all right? When you and I, we actually interact with mixtures of gases way more often than pure gases. So the nice thing about when we're working with mixtures is we can Pivnert them individually or Pivnert them all together, all right? So what I mean is that when you have a mixture of gases, let's say nitrogen and oxygen in the same container, nitrogen exerts a partial pressure. Oxygen exerts a partial pressure. Those partial pressures add up to give you a total pressure, all right? So we can treat them individually because we can count how many moles of nitrogen we have, we can count how many moles of oxygen we have to then calculate pressure if we know temperature and volume. So the idea of mixtures is you can treat them individually or collectively. So in this question, we have a vessel with an internal volume. There's my volume. And I have 3 different gases. I have nitrogen, hydrogen, and argon. And then here's my temperature. What is the total pressure inside the vessel? So if I want the total pressure, all right, so PV equals nRT. If I want the total pressure of the system, I need to figure out how many total moles of gas I have, right? We have 3 different gases. So we need to convert all of these into mole amounts, all of them, and then add them up. But thankfully, I think the numbers are pretty easy. All right, I think the numbers are really easy. I tried to make it easy. So 2.8 grams of diatomic nitrogen is 0.1 moles of nitrogen, all right? Because I think the molar mass is like 28. And then what, 0.403 grams of hydrogen. I think that's 0.2 moles of hydrogen. Sorry, sig figs kind of just went out the window here. And then finally, 79.9 grams of argon. This is 2 moles of argon, right? So you have 3 different gases here. So 0.1 moles, 0.3 moles, 2 moles. So the total number of moles of gas that we have total in this container is 2.3 moles of just gas. all right? And so when we Pivnert this number using the information given in the problem, that is what gives us our total pressure. And if you do that, I think you get something like 5.62 atmospheres, right? That's the total pressure. All right, and then finally, which gas possesses the largest mole fraction in the mixture? We can probably determine this without even calculating anything. Just look at the mixture right now. There are all my mole amounts. Which substance is present in the largest quantity in mole amounts? It's argon, all right? So argon has the largest mole fraction. You could calculate it, all right? The mole fraction of argon is equal to 2 moles over 2.3. I think that's equal to 87%. All right, so our sample is 87% argon, which also means the partial pressure of argon is 87% of the total pressure, so 5.62. If just the argon was exerting pressure, it would be 87% of that total amount. All right, so that's partial pressures. Okay, all right. Good, all right. So let's do this one real quick. Okay, which of these gases has this density at this temperature and this pressure? All right, so when approaching density, I always let the unit guide me. Understand that density is just the mass of your substance over the volume of your substance. All right. So what I like to do with density, since we're not given amounts of helium, argon, or xenon, I always like to assume we have 1 mole of your gas, all right? So if you assume you have 1 mole of gas, you can figure out, okay, how much does 1 mole of gas occupy at this temperature and pressure? That volume goes in your denominator, right? If we're working with helium, do you know how much 1 mole of helium weighs? Yes, you do. That comes from the periodic table. So whenever you're trying to calculate density of a gas, you always need to start with some amount. But typically in the question, we don't give you the amount, so you have to make up a number, and the easiest number to work with is 1 mole. Just pretend you have 1 mole of helium, and ask yourself, how much does 1 mole of helium weigh? Then you ask, how much does 1 mole of helium occupy in terms of volume at this temperature and pressure? And that number goes on the bottom here. So if we actually do that, if we plug in this temperature, if we plug in that pressure, we get that the molar volume is equal to something, it is equal to 18.98 liters, right? So we can actually do this very, very simply. Once we get that volume of 1 mole of gas, we can actually calculate the density of all of these gases real quickly. All right, the density of helium is going to be the mass of 1 mole of helium. So what is that? It's about 4.003 grams over that volume we just got, 18.98 liters. So we see that this number does not equal the 2 grams per liter that we're trying to get. All right. Next, we can do argon. The density of argon is equal to the mass of 1 mole of argon. What is that? Is that like about 40? Yeah, it's like about 40 over 18.98 liters, and this is very, very close to 2.104. So that is our correct answer right there. Argon has that density. Just for completeness, let's calculate the density of xenon as well. The density of xenon at this temperature and pressure. 1 mole of xenon weighs how much? I don't know. It is 131 grams over 1 mole of xenon occupies 18.98 liters. So we see that this number is way too big. This is about like 7 grams per liter. So that's way too dense. All right. So that's our strategy there. So I had to calculate it 3 times, 3 different densities to find the right answer here. All right. But my strategy here for calculating density of gases is start with an amount, Just assume you have 1 mole of gas. You can figure out how much 1 mole of gas occupies in volume. You can also figure out the mass of that sample of 1 mole of gas given its formula. All right. Okay. So, with gases, we know PV equals nRT. N is our mole amount. Remember all the fun we had with moles in chapter 3, stoichiometry. So none of that changes in this chapter when talking about gases. So mole amount of gases still have to follow stoichiometry rules and coefficients that we have here. So here I have oxygen gas. It's being generated by this reaction. So I'm telling you how much gas I'm collecting, and I want to know how many grams of reactant were consumed here. So if this were chapter 3, it would be me saying, oh, how many grams of reactant you need to make this many grams of product. But notice oxygen is a gas. We rarely measure gases in gram amounts. Instead, we measure gases in terms of their temperature, pressure, and volume. So we're going to PV equals nRT, our oxygen information. We're going to use that N amount. We're going to do stoichiometry to get our where we want to go. In this case, it's the reactant, right? So using this information, I give you everything we need to know about oxygen. There's its volume, there's its temperature, there is its pressure. So we can figure out how many moles of oxygen were generated in this reaction. So I'm gonna just rearrange PivNert real quick. I think I can do that, PV over RT. So the mole amount of oxygen that was collected is 1 ATM. Because it's 760 torr, I just converted it in my head. 2 liters over R, it's a constant. We do give this to you. It's in the packet or in the supplemental information somewhere. Mole Kelvin. And then temperature, so 27 plus 273 is exactly, it's 300 Kelvin. All right, so all of that together, I get that the mole amount of oxygen that I generated in this reaction was 0.08124 moles of oxygen. Now, at this point, after I PivNerted, it is no different than stoichiometry in chapter 3, right? So I have a mole amount of product. I want to figure out how many grams of reactant do I need. So I'm simply going to do stoichiometry. So notice the coefficients, 2 and 3. Where's the 3 going to go, on the top or the bottom? Bottom. 3 moles of oxygen requires 2 moles of KClO3. Now, how do I get to grams? Molar mass of what? KClO3. So I didn't give it to you, but I'll just tell it to you now. It's 122.55 grams per mole. All right, that's the molar mass. So the 122 goes where? On the top or the bottom? Top. 122.55 grams, 1 mole of that reactant, KClO3. And then you get some answer there. All right, so this last step, this is no different from chapter 3. All of this is not new to you. The only new thing was this right here. So recognize that PivNert is another way we can ride the bus of our balanced chemical equation to use these coefficients. Back in chapter 3, we used gram amounts, and we used molar mass to get to the unit of moles. In chapter 4, when we worked with molarities, molarity allowed us to get to mole amounts to use the balanced chemical equation. So now in chapter 10 with gases, we're using PivNert to get to moles to use the exact same balanced chemical equation. So none of that is different. The only thing we're adding here is PivNert. All right, keep going. Okay, so let's do this last part with kinetic molecular theory and just kind of recognize some trends here. For gases. Gases, they're moving around like crazy idiots. In a gas sample, typically they move in straight lines. We assume they have no volume, but we see that that tends to break down at high pressures. We know that the temperature of our sample is the average kinetic energy of our sample. So when we think about the typical speed of our sample, it has to relate to the mass of each of the particles in your sample. So here, which gas possesses the faster RMS speed at room temperature? Since both of these samples are at room temperature, they have the same kinetic energy, right? If they have the same kinetic energy, just remember the equation for kinetic energy. It's equal to 1/2 mv squared, all right? So if I have a light particle, a very lightweight particle, it's going to have a very fast velocity versus if I have a really large particle with the same kinetic energy, it's going to have a slower velocity. So what we see here is that neon has the faster root mean squared velocity because it is a lighter particle. All right. RMS is a little bit different than average speed. Average is a statistical term because you would have to actually measure every single speed of every particle, and that's just not feasible to do. But RMS speed tells us that same trends. So we can also say, yeah, the average speed of a neon sample is faster, but when we're thinking about the sample and measuring it in terms of temperature and its molar mass, we typically use RMS speed instead. All right. Okay, so there is that. So the kinetic energy equation will tell you the trends that you need. All right, so at what temperature will oxygen possess the faster RMS speed? Hotter things have more kinetic energy. So they're going to be moving faster. So again, if you bring this back to your kinetic energy equation, having a higher temperature increases your average kinetic energy. So it increases this number, increasing your effective speed, while mass is staying the same because our sample is staying the same. All right. Okay, which gas will effuse faster? So effusion is proportional to collision rate, which is proportional to speed. So basically, particles that move faster are going to effuse faster. So neon is going to be effusing faster here. You've probably seen this if you've ever gone to like the aftermath of like a big party where there's helium balloons. You might see that some of the balloons get a lot smaller faster. Helium balloons, like when you buy them from like the party store or whatever, because helium is such a lightweight particle, and we take advantage of that because, you know, those helium balloons float. What you'll see is that helium balloons deflate a lot faster than like regular balloons that you blow up with like your regular lung air. All right, so if you can do that experiment at home if you wanted to, like take a helium balloon, take like the same balloon, but just fill it up with your lung air and just like leave it somewhere, and you'll see the helium balloon get smaller a lot faster. It effuses faster because the particles inside it are a lot more lightweight, versus our lungs are mostly like, you know, CO2 and oxygen. They're a lot heavier, so they effuse not as fast. All right, so let's keep going. Which gas possesses the greater density at STP? So at standard temperature and pressure. So remember, density is equal to mass over volume. So just make the assumption, let's work with 1 mole of gas, 1 mole of argon, 1 mole of neon. They will have the exact same volume, but what will be different? Their masses. All right, so what we see here is that argon has the heavier density because it has the larger molar mass. All right. All right, and then finally, these last two have to do with, so does RMS speed have to do with only size of the atom? Nope, it's size or mass and temperature. Mass and temperature. There's an equation for it. I'm not sure, is it given? Is RMS speed given? It is, yeah. So the equation for RMS speed, which really is just very similar to this kinetic energy equation. So RMS speed is equal to square root 3RT molar mass. So we see that the factors to RMS speed are temperature, So increased temperature, increased RMS speed, and then molar mass, increased molar mass, so heavier objects have slower RMS speeds. All right. And then finally, here are deviations from ideal behavior. Which gas deviates more from ideal behavior at high pressures? All right, so at high pressures, your size of your particles start to matter, right? I like to think of it this way. In order to achieve a high pressure, you have to shove a ton of gas into a small space, right? So if you have a lot of gas in a small space, the size of those actual particles start to matter. So if you shoved a lot of tiny, tiny, tiny particles, like tiny grains of sand into a container, the size of the particles of sand don't really matter. But if you shove like a bunch of ping pong balls into a container, that size does matter. So which one matters more, argon or neon? Argon, why? Because it's bigger, yes, because it's bigger. There's our ping pong ball. All right, and then finally, which gas possesses the larger A term? What does A stand for? Attractions, yes. And actually, E, the previous one we just did really was the B term. We actually just did the B term. I just didn't like outright say it. So this last one, which one has the larger A term? Diatomic nitrogen, or CO, right? So attractions, this goes right into chapter 11 with intermolecular forces. We see CO, it is a polar molecule. It's going to have more attractions. We can't really use weights here because both of these particles have the same molar masses. They both have 28 grams per mole for their molar mass. All right, let's just keep speeding through this. All right, so that was chapter 10. Now chapter 11, one of my favorite chapters, intermolecular forces, because it really rounds out Chem 1210. We learned about composition a lot in the beginning of the semester. At the end of the semester, we look at structure, molecular geometries, and now we get to see how does structure and composition affect chemical properties that we see, all right? So when looking at intermolecular forces, there's three. There's London dispersion, dipole-dipole, and then hydrogen bonding, right? They increase going down. So London dispersions are the weakest, then it's dipole-dipole, then it's hydrogen bonding. Usually the strongest one dictates your properties. So if you have a molecule that can hydrogen bond, its ability to do London dispersion isn't as important, all right? But if you only have a molecule that can do London dispersion, then that's gonna be really important. So of each of these three things, they trend differently. For LDF, it's molar mass, and then also surface area, all right, surface area. I'll point out that linear things, long skinny things have large surface area, therefore they have large London dispersion forces, all right? All right, next, dipole-dipole, you're looking for polar things, all right? So if you have a polar and a non-polar thing, the polar thing's gonna win in terms of attractions, their intermolecular forces. And then finally, hydrogen bonding. This one's tricky, all right? Because students, they love to, whenever they see a hydrogen, they're like, ooh, that can hydrogen bond. But no, it has to be a special hydrogen. It has to be a hydrogen that's really electropositive. How do you make an electropositive hydrogen? By attaching it directly to a oxygen, to a nitrogen, or to a fluorine. Fluorine, all right? That is what you wanna look for, okay? You can't have a molecule that has oxygen here, hydrogen over here, and it can hydrogen bond. No, it has to be a hydrogen attached to an oxygen, all right? Here's an example. If I drew this, O, C, with like a bunch of H's, okay? C with a bunch of H's. You might be like, oh, Dr. N, there's an O and there's an H. This can hydrogen bond. No, it can't, because is the hydrogen attached to the oxygen? No, it's attached to what? A carbon. So this is actually a very non-polar carbon-hydrogen bond. It's just, this molecule would just be polar. It would have dipole-dipole. It would not be able to hydrogen bond. So yeah, for hydrogen bonding, what you're looking for are these specific groups, OH groups, NH groups, or HF. All right, okay, so let's go through this. Okay, so with all of that, then let me just put together all of the trends, okay? Intermolecular forces just means particle attraction. What you need to get through your mind here is that we're not breaking bonds, we're just separating particles from one another. All right, we're just separating this water molecule away from this water molecule. So when we see intermolecular forces, attractions increase, what we'll see is that normal boiling point temperature will increase. All right, it gets harder to boil your sample because when you boil stuff, you're breaking all of the intermolecular forces. So if your particles are really attracted to one another, you're going to have to get your sample ripping hot to get it to boil, right? What we'll also see is that delta H of vaporization, sublimation, and the other one, fusion, all of these numbers increase for things that are attractive. What else is there? Viscosity, oh, thank you. Thank you for doing my job for me. Viscosity increases. What is viscosity? Resistance to flow, all right? I like to think of it this way. If your particles are really attracted to one another, will they like to flow past one another? No. So if there's lots of intermolecular forces like honey, okay, honey is a very, very heavy molar mass substance, then it's gonna flow really slowly, all right? But a way that we can improve viscosity, make things flow faster, is by heating it up, right? Like if you take maple syrup out of the fridge and pour it, it pours very slowly. But then put it in the microwave and then take it out and then pour it out. We see that extra temperature, kinetic energy, allows particles to move more freely past one another, improve its viscosity. Okay, what else is there after viscosity? Surface area, thank you. Or not surface area, surface tension. Surface tension. Okay. And then the last one, vapor pressure. All right, we see everything increase as IMFs increase except vapor pressure. Vapor pressure decreases when intermolecular forces increase. What is vapor pressure? I like to associate with smelliness, all right? So if I put nail polish remover under your nose, what face do you make? Yeah, gross, right? But here's the thing, nail polish remover, it's a liquid, right? It's a liquid, but why are you making a face? Gases, smells, they're gases, right? So how is nail polish remover, which is a liquid, how are you smelling it when it's a gas? It's because all liquids exert a vapor pressure. All liquids let some of their particles go into the gas phase, all right? Everything. But some more than others based upon the extent of their intermolecular forces. So think of it this way. You have a liquid, sometimes the liquid lets their particles go into the gas phase. If the particles are really attracted to one another, will they let their friends go to the gas phase? No, they won't. But if your particles are not very attracted to one another, will they let their friends go to the gas phase? Yes, they will. So acetone, that's what nail polish remover is, has low intermolecular forces. It has a high vapor pressure. So we say it has a high volatility versus things like water. Does water smell like anything? No. Water has a very low vapor pressure at room temperature because it has very high intermolecular forces, right? So yeah, so basically if we ask any one of these properties, all of it just comes back to intermolecular forces. If I ask you which one has the greater viscosity, what are you actually looking for? IMFs. If I ask you which one has the highest vapor pressure, you're actually looking at IMFs. That's it, right? So all of it comes back to IMFs. So for these substances, these number 10, which substance has the higher normal boiling point temperature? So what am I actually choosing? The substance with the least IMFs? No, most IMFs, yeah. So high boiling point, just think about it. High boiling point means hard to boil, hard to separate, right? So we want to choose the thing where the particles are most attracted to one another. So let's look at the first one. You need to figure out which one of these IMFs is kind of the dictating thing here, all right? So what do I notice here? I got a bunch of carbons and an NH group. What does that mean? H bonding, yeah. What about this guy? This guy also has an NH group and another one. So which one has more IMFs? The second one, because it can hydrogen bond twice. Perfect. Okay, BR2 or ICL? It's going to be ICL. Why? Because it's polar. BR2 is nonpolar. Okay, PH3 or ASH3? Both of these things are polar. They're both polar. Neither of them can hydrogen bond. So what I'm going to go for here is just weight. All right, that ASH3 is a lot heavier. It's a lot heavier. Okay, both are polar, both can't hydrogen bond, so I'm just going at weight. And then the last one here, BR2 or XE, xenon. So both of these are nonpolar. So you might want to look at molar masses. Can I calculate this? Bromine is about 160. Xenon is 130. So here we see bromine is heavier. Also, bromine is heavier, but it also has more surface area. It's a linear molecule, so that also adds to its improved or its increased intermolecular forces. All right, so the mass and the surface area of it. All right, perfect. Okay, so in this next one, which of these substances has the highest vapor pressure at 0 degrees Celsius? So we know it's related to IMFs, but remember, what kinds of things have high vapor pressures? What kinds of things are smelly? Low, yes, low intermolecular forces, because if the particles are not friends with one another, they will let their particle friends go off to the gas phase so you can smell them, all right? So yeah, we are actually looking for the lowest IMF here, right? Or I could say, you know, which substance exerts the lowest vapor pressure or something, then we would look for highest IMF, all right? But here we want lowest. So CCl4, CBr4, so all of these things are non-polar. So we're just gonna look for molar mass. So CCl4 is lighter. All right, next one. This hydrocarbon, is this polar or non-polar? Non-polar, because it's all hydrogens and carbons. But then this thing, we got a bunch of carbons and hydrogens, and then a chlorine tacked on the end. This is polar, yes. I don't even have to draw it. I know that chlorine is gonna screw up the symmetry, screw up the dipoles. This is polar. So what are we picking? Lowest IMF, so it's this one. Yeah, I forgot what we're doing. All right, last one, H2O and H2S. This one's tricky because you might look at this and be like, oh, H2S is a lot heavier, that has more IMFs, but what's special about water? Hydrogen bond, yeah, this can actually hydrogen bond, all right? H2S cannot hydrogen bond. Basically, it just has dipole-dipole. So what are we trying to do? Highest vapor pressure, so it's gonna be this one. It's H2S. All right, because we're looking for the lowest IMF for all these pairs. All right, got it? I can change any of these questions to like one of these. I could say which one has the highest viscosity, which one has the highest delta H of vaporization, and the strategy is still the same. All right, last one here. Oh, two more. Which substance exerts the highest vapor pressure at their respective normal boiling point temperatures? All right. Okay, so this one's tricky. I'm just gonna tell you the answer, it's D. All of them exert the same vapor pressure at their normal boiling points. You need to understand why. Why does water boil at 100 degrees Celsius? You ever wonder why? It just does. So here's the thing, water boils at 100 degrees Celsius because at 100 degrees Celsius, water exerts a vapor pressure of 1 atmosphere. We live on Earth, which is 1 atmosphere, right? So once your substance has a vapor pressure equal to the external pressure being pushed on it, that's when your substance will boil. But in a pressure cooker, anyone cook with a pressure cooker? They're great, right? It cooks stuff faster, okay? Why does it cook stuff faster? Because we're cooking under pressure. There's more pressure inside that pot. So water actually has a higher boiling point temperature, that it has to exert a higher vapor pressure before it starts to boil because the external pressure is greater on it. Or think about Denver, the mile-high city, all right, has a lower a lower external pressure than normal. Its atmospheric pressure is about 0.8. So water actually boils at like 95 degrees Celsius up there, all right, because there's just less pressure. So what we see here is that anything will boil as long as its vapor pressure is equal to the external pressure on it. But what's very important about this question is I say normal boiling point temperature. So when we talk about boiling points here in this class, 99% of the time we're talking about normal boiling points. I want you to tell me what is the boiling point of this substance on Earth when you do it on the benchtop in lab, where it is 1 atmosphere. But I do want you to understand that if we went to Denver and did all these boiling experiments, you would actually measure different temperatures because the external pressure there is different. But here I say normal, so that implies, 1 atmosphere of external pressure, all right? So that's implied here. Normal, we like to say earthly things are normal, so that's 1 atmosphere. So that one's a trick question. Anything will boil on Earth when the vapor pressure is equal to 760 torr. All right, perfect. Okay. Okay, 2 more here. Which statement is false about viscosity? Viscosity increases as temperature decreases. No, that is false. Wait, hold on. Is viscosity things that flow slow? What is it? I forget. Yes, okay, all right. So the definition, viscosity. Yes, resistance to flow. All right. I have to remember my oil weights. So things with high viscosities, we typically use like SAE ratings. So high viscosities means flows slow. Yes. So A is correct. All right. At low temperatures, if you have cold maple syrup, it's going to flow slow. So it actually has a high viscosity. All right. So that is true. B, viscosity increases as molecular weight increases. This is true as well. Remember, because as IMFs increase, viscosity increases. So molecular weight, that is a general term for saying, oh, your attractions is increasing. Viscosity is C is also saying the same thing. Viscosity increases as intermolecular force. Oh wait, no, that one's not true. Yeah, that one's false. That's the false one. Sorry, my brain was saying the correct words. Yeah, so C is the false one. But let's just go through all of these. Viscosity is resistance to flow. Yes, that's true. A highly viscous substance flows slowly. Yes, so that's true. Sorry, I forgot. I had a brain fart for a minute. Okay, good. All right. Okay, just a couple more, and then we're done. All right, so the following is an unlabeled phase diagram. What's the approximate normal boiling point temperature for this substance? So when given a phase diagram like this, the bare minimum what you need to know are the regions. What region is this? Solid, very good. What region is this? Liquid, and then the last one's gas. Yes, all right, perfect. The points you need to know right here, this is your triple point. This is the point where your solid, liquid, and gas all exist at the same time. It only happens at one specific pressure temperature combo. That's your triple point. Here, this is your critical point temperature, meaning that this is the minimum temperature you need, so 300 Kelvin. If your sample is above 300 Kelvin, it's going to exist as a supercritical fluid, meaning it's like a really energetic gas that can't be liquefied, right? But anything lower than 300 Kelvin, you can have a solid liquid or gas, but anything above it, you have like a crazy supercritical fluid. All right, perfect. So that's what you need to know about this diagram. Anytime you move across any one of these boundaries, you have a phase change. All right, so what is the approximate normal boiling point temperature? What did we just say? What does normal mean? 1 ATM. Normal means Earth. So I'm asking you, at what temperature does our sample boil? But since I say normal, that's how I'm telling you what pressure. Because notice, our sample will boil anytime it crosses this liquid gas boundary. But I'm being specific here. I am telling you, I want you to tell me, when does the liquid gas boundary happen at 1 atmosphere, 760 torr, because it's normal boiling point temperature. So that happens right here. Right, so right there, I don't know, that's like 175 Kelvin, I guess, something like that. Right? Its melting point's going to be a little bit lower than that, like 150, okay? So on Earth, this substance boils at 175 Kelvin. If we went, you know, somewhere with a really, really crazy high pressure, it would boil, it would actually be, it would actually never boil. It would just become a supercritical fluid. All right. Or somewhere where a very low pressure, we would see that the substance would sublime instead. So yeah, our answer probably C, 170 Kelvin. All right, perfect. Oh, I'll just point out E, this substance has a sublimation rather than normal boiling point. That would be true if 1 atmosphere happened like one right here. If 1 atmosphere was right here, then we would do the same thing. Oh, draw the line, but the only phase change happens right here, and it's solid to gas. So if 1 happened right here, this substance would sublime. An example of that would be CO2. We call that on the street dry ice. Dry ice doesn't melt, it just sublimes straight into a gas. That's why it's called dry ice. So that's solid CO2. Okay, all right. So using the same question, the same diagram, what phase change occurs at this atmosphere, this pressure? So we just need to be really careful and find where that is. So 0.1 ATM, that is 10 to the negative, how many? 2, thank you. So somewhere right here. And then 220 Kelvin, so yeah, I think it's right here. Oh yeah, so what phase change is that? Sublimation, right? So if we were at this temperature and pressure, we could calculate delta H of sublimation. All right, that is where your gas and your solid are at equilibrium, and you can calculate that enthalpy term. All right, okay. All right, okay. Last 2. So I think this is actually a chapter on solids. So let's arrange the following substances in order of melting points. All right, so we're really just looking at intermolecular forces here. Right? So higher intermolecular forces, the higher your melting point temperatures, because more attractions, harder to separate those molecules from one another. So we want to look at these samples and think, what is the dominating intermolecular force? So let's work backwards. Let's do right to left. This substance, what is the most important IMF? H bonding. How do I know? OH. Perfect. We don't do that here. CH4, what's the most important one? London dispersion. Perfect. LIF, we haven't talked about this one in chapter 11, but we did in chapter 12. LIF is what kind of solid? Ionic, yeah. So don't forget chapter 2 stuff, right? Just look at the substance and be like, how would I name that? Right? If this was chapter 2, how would I name that? You would call it lithium fluoride. You follow ionic naming rules. It's an ionic compound. Right? So just think of attractions. Ionic compounds have a really, really, really high attractions to one another, electrostatics. So we're actually going to see that this ionic compound has the most attractions to one another. It's going to have the highest melting point temperature. Also think when you interact with ionic stuff like salt, NaCl, when you interact with that on the street, what phase is it in? Solid, yeah. So if it's a solid, does salt have a low melting point or a high melting point? It's high, yeah. So ionic stuff tends to have very high melting point temperatures. So the ordering of this, what's increasing normal melting point? So it's going to be CH4, then it's going to be CH3OH. These are both molecular compounds. They have low melting points, but this one wins because of H bonding, and then it's going to be LIF. All right, the reason these are ionic, these are molecular. All right. Okay, so this question says, question 12, every substance have the same vapor pressure at the normal boiling point temperature. That is correct. Yes, at their respective normal boiling point temperatures. Okay. We check for IMFs if it's different samples at the same temperature. Like if we were smelling water and vinegar, both at room temperature, we just compare intermolecular forces. Ionic solids always have greater melting points. Yes. So let me just for a second switch to my slides. Just going over solids real quick. Go over solids real quick. Okay. So here are the properties of the 4 different types of solids. So we got metallic solids, ionic solids, covalent network solids, molecular solids. So if we just look at ionic solids and molecular solids, so ionic things, because of their electrostatic attractions, they have very high melting points. Molecular solids have very low melting points, all right? So how do I know something's a molecular solid? If we asked you to draw a Lewis structure for it in chapter 8, it's a molecule, it's a molecular solid, all right? So any of those things are going to have those molecular solid characteristics. Right, and then here are some of our other solids. I've highlighted in this slide what I think are the important properties that kind of give away that substance. So for example, metallic solids, metals, their solids conduct electricity. But ionic solids like NaCl salt, like salt, technically salt in the solid phase does not conduct electricity because salt, even though it's made of cations and anions in the solid phase, they can't move. They're stuck there. But once you dissolve salt, it conducts electricity because now those ions are free to move in water, right? If you melt salt, if you melt it and make it molten in the liquid phase, now those ions can freely move. In the molten state, salt also conducts electricity, but in the solid phase, it does not. And that's very important here. And then interesting things about covalent network solids is they tend to be insulators. And they're very, very hard and have very high melting points and boiling points. So let's just do this slide real quick. All right, so if we have a solid, it's soft at room temperature, very soluble in water, solution does not conduct electricity. It is most likely to be a what? What do we think? It's going to be a molecular solid. How do we know? The giveaway, soft. Very soft. Okay, and it dissolves and the thing does not conduct electricity. That's the giveaway. All right, the next one, solid that's shiny and malleable, completely insoluble in water, but the solid does conduct electricity. What is it? Metallic, very good. Last one, here, this one's a little bit different. Here I'm giving you a substance, NABR. What is that? That's ionic, so what characteristic is it gonna have? Is it gonna be a gas? No. A liquid? No. It's going to be a solid, but which one? It's going to be a brittle solid. Yay, yeah. What's the one that if you got this wrong, what did you want to say? Conducting solid, you want to say conducting, but do ionic solids conduct? They do not. You have to dissolve them or melt them to make those ions mobile. All right, let's go back to the packet, but I hope that clarifies those properties. Okay, because I think there's one more. Okay, perfect, all right. Okay, so here's the last one, and then we're done with new stuff, and then we can do old stuff. All right, the electrical conductivity of a white, soft solid. What is it? What is it? It's probably molecular, yeah, probably. It's found to be highly insulating, yeah. When solid is added to pure water, it dissolves completely, so that kind of eliminates metallic stuff. It eliminates covalent network, and the solution does not conduct electricity, yeah. So I would say this is molecular, my friend. This would be sugar. This would be sugar, right? All right, do we feel better about solids now? Okay. Okay, what are people saying in the chat? Does a high vapor pressure mean the substance vaporizes easily? No, high vapor pressure usually, well, yes, that means that if it has a high vapor pressure, the liquid converts to a gas fairly easily. But typically the language that we use is we say that the substance is volatile. I can't spell volatile. Yeah, there we go. All right. So liquids with high volatility tend to have high vapor pressures. They are smelly to us. Like if you've ever gone to the hardware store and bought paint, many times the paint on the can, it'll say, oh, this paint is low in VOCs. What VOC stands for is volatile organic compound. When we think about painting, usually it's a smelly process, and so those products just eliminate some of the smells, the high vapor pressures that come from some of those things. Okay, so we're done with 9 through 12. All right, what do we want to do now? What chapter? Is there a specific question someone wants to do? Just yell out the number. Can we go in order? Okay, we'll just go in order. All right. Okay. We'll go in order until someone yells out a number. All right, so midterm, this is old stuff. So this is chapter 1. Report the following to the correct number of significant figures. All right, so when most students look at this, they count sig figs, and they go, oh, this one has 3, so my answer must have 3. Is that how we do it? No, we don't, because this is mixed operation. We have to do it step by step and recognize that there are different rules for addition, subtraction. That's the one everyone forgets, all right? So I will make it my mission to make sure that if you just simply count sig figs, you will be wrong on the exam. You will be wrong if you just count sig figs. That is only when it's multiplication division, but this is mixed operation. So we'll do the multiplication first, where we do simply just count sig figs. So this one has, this first number has how many? Just yell it out. 5, and then the other one has, it does not have 4, 1.5630. Why did I take the time to write that 0 if it wasn't significant? All of the numbers are significant. So when we're talking about numbers with decimal places in it, if I write the 0, I took the time to write the 0, because like, how is 1.3 different than 1.30.30? What's the difference? The difference is probably $100 in terms of equipment in the lab to get more decimal places. All right, so these numbers have different significance to them. So the second one actually has 5 sig figs. All right, so that means our answer to just that first multiplication is going to have how many? 5, yeah, so when you do that, it is 6.03646, but I'm just gonna underline the last sig fig, all right? So if I was done, I would round to the 4th decimal place, but I'm not done. I still have to do the subtraction, so minus 5.98, all right? So I'll underline all of the significant digits here, all of the significant digits here. So when we report our answer, what is the last place value we can accurately report? The second decimal place. Why? Because that is the last place value that both numbers share. That's why, right? I like to say, oh, all the numbers after that 0.98, they're fuzzy. They're fuzzy. I don't know what they are. Do you know what 6 plus fuzz is? No, so you can't report it. So that means all these numbers are fuzzy. So when you report this, the answer is 0.006, and that's it. That's it. So, A. So if you simply count sig figs for this question, will you be right? No, because our answer has one sig fig at the end, and the reason comes from that addition subtraction rule, right? Where we can actually lose or gain sig figs because it's all about place values. All right, okay. Okay, let's just do this one real quick. All right, 3 students conduct an experiment, mass of a gold coin, here are the results. True mass is blah. Which student is most accurate? What determines accuracy? The true value. So what are we comparing? We're comparing the average of every student to the true value, all right? I don't feel like calculating it, right? So just average all of the students, figure out who is the closest to the true value. It's right here, all right? Then which one is the most precise? What does that depend on? Precision? Range? I like to say range. Basically, you're going to look at the high and the low in the data set and just see what the range is. So student C, they have a really narrow range. Their range is only like 0.1. They only deviate a tiny, tiny bit. But who has a really bad range? Who's really awful? This student A, that one's probably me. See, here's the low, 62.1, and here's the high, 63.9. So this student, they deviated what, 1.8? That's crazy, 1.8 grams in their measurements, right? So that's their range. So in this case, I think student C would be the best in precision. If I didn't tell you the mass of the gold coin, which one of these could we not answer? We couldn't answer accuracy, but we could still answer precision, right? We could still say, oh yeah, one of these people are more precise. All right, okay, so someone wants to do question 23 and 24, so I'll do that. Okay, where's 23, 24? All right, and then someone else said they just want to do chapter 3. Okay, so fine. All right, so we'll just keep going in order then, I guess. All right, so here we have a diagram of a mixture between sulfur atoms and oxygen atoms inside a closed container. Here is the reaction. 2S plus 3 oxygen gives us 2 SO3. Which diagram shows this? So I want to count how much of each thing I have. There's a couple ways I can do this. Recognize, I need 2 S's and 3 O2s to do this reaction once. So I can do it this way. Okay, let's do the reaction once. There's an S, and then there are 3 O2s. So I do the reaction once. I gain 2 SO3s. Then I try to do the reaction again. So here is an S, there is an S, 1, 2, 3 O2s. So there I gain another set of SO3s, all right? Can I do the reaction again? No. So in my container, I have 4 SO3s, but also notice I have 2 S's left over, all right? That I didn't touch, so they're still there, So you are gonna look for the picture that depicts this. 2 S's and 4 SO3 molecules, and so which one is that? That is D, right? Another way we can do this is use a BCA table. We can count everything, 1, 2, 3, 4, 5, 6. There's 6 sulfurs, and then 1, 2, 3, 4, 5, 6 O2s. So just looking at these numbers, you can do the reaction 3 times with sulfur. How many times can you do it with oxygen? Twice. So which ones limits us? Oxygen. So I'm going to completely consume oxygen, so -6. So if I use up 6 oxygens, how many sulfurs do I also consume? minus 4, yes. So notice that this ratio is the same as this ratio. And then, so if I consume 4 sulfurs, I gain 4 SO3s. So when you add everything, we get the same exact thing. We have 2 sulfurs left over and 4 SO3s left over, right? So the answer is D. That's the one that shows the 4 SO3s. Common misconception is this one, right here, this one. They look at, we look at the reaction, we go, oh yeah, we can do this reaction twice. If we do this reaction twice, I gain, I do this 2 times. But notice that this molecule, what does this molecule depict? It depicts 2 sulfurs bonded to 6 oxygens. But notice here, SO3, that's a single molecule. And this reaction is just trying to tell you, oh, you make 2 of them, 2 separate molecules. So don't pre-combine that molecule, because remember, molecules exist as these discrete things. The coefficients just tell us how many of them we make, right? Okay, so yeah, we're just going in order. So that's 20. All right, 21. Here's caffeine, here's the formula, here it's molar mass. Okay, so this is just molar mass stuff. So how many nitrogen atoms are present in a 250-gram sample of caffeine? So our strategy here is to use molar mass and Avogadro's number and the chemical formula where necessary. So notice we are given the gram amount of caffeine. So when I choose a molar mass, I want to use the molar mass of caffeine because I'm starting with the gram amount of caffeine. So 194.19 is going to go on the bottom, gives us 1 mole of caffeine, right? But I don't want caffeine, I want nitrogen, right? So we can look at the chemical formula. One of these things is a caffeine. How many nitrogens are there? 4, yeah. So in every 1 mole of caffeine, how many moles of nitrogen are there? 4, yes, 4 moles of nitrogen. Am I done? Nope, what do I gotta do? Avogadro's number, yeah, so just Avogadro's number at 1 mole of anything, in this case it's nitrogen, is 6.022 times 10 to the 23 N atoms, right? I don't feel like getting the answer, you just look at the key. All right, so this one is actually the same question, but it's backwards. But this question would probably get 80% of students would get this one right, but only like 50% of students would get this one right. This one's backwards. So let's just work through it. We're going to use that same strategy. So we have a caffeine sample, but this time I'm telling you it contains this many hydrogen atoms. How much does the sample weigh, the caffeine sample weigh in total? So I'm starting with hydrogen atoms. So a lot of students will recognize, oh, I need to use Avogadro's number to put that into moles. Like they'll get that right away. So let's do that. Let's get the atoms into moles. 6.022 times 10 to the 23 atoms. Hydrogen atoms gives us 1 mole of hydrogen. So now I'm in moles of hydrogen. What a lot of students will do is do this. 1 mole of hydrogen weighs 1.008 grams. But if I do this, I'm calculating the mass of what? Hydrogen. Is that what the question's asking for? No, I want the mass of caffeine, yes. So should I just put the caffeine molar mass here? We can't do that. We need to figure out how many moles of caffeine we have. Right now we have the mole amount of hydrogen. So the step that I'm missing is this step right here. Remember when we said, oh, 1 caffeine molecule has 4 nitrogen atoms. So we're going to do the same thing, but the other way. 1 caffeine molecule has 10 hydrogen atoms. So where am I going to put that 10? On the bottom. 10 moles of hydrogen is 1 mole of caffeine. Now, can I use the molar mass of caffeine? Yes, you can. All right. So 1 mole on the bottom of caffeine 194.19 grams of caffeine. So notice, step by step, it's backwards. We did it backwards, all right? So do not forget this scaling step, that comes from the chemical formula. Okay, all right, keep going. So 21, we gotta make it to 25 or something, all right. Okay, what is the empirical formula for a compound that's that and that by mass? What's our strategy here? When given percentages, what are we gonna assume? 100 grams, because then those percentages just become gram amounts. So we have 81 grams of fluorine, 19 grams of carbon. We're gonna use molar mass and just convert that to moles. I don't feel like writing it out. All right, so use the respective molar masses. We see that this sample has 4.26 moles of fluorine, 1.58 moles of carbon. So is that my formula? Nope, what do we have to do? Divide by the smallest one. Why the smallest one? Because this ensures that at least one of the ratios is 1, which is an integer, and that's what we want. So for every 1 mole of carbon, we get 2.696 moles of fluorine. So should I just round this to 3? No, this is very close to 2 2/3. Okay, 0.66, that's 2/3, all right? So to get rid of that fraction, we're not gonna round. We're not gonna round, what are we gonna do? Multiply everything by 3, yeah, so 2.68 or whatever, 69 times 3 is very, very close to 8. It's like 8.03. So this is F8C3, or C3F8, whatever, all right? Good, all right, so this one. So this one is a limiting reactant question. Okay, calculate the mass of excess reactant remaining when 90 grams of SO2 reacts with 100 grams of oxygen. All right, should we do it BCA table? Do you want to do, no, okay, all right. Okay, all right, so, okay, let's not do a BCA table. My strategy is, we're given SO2, we're given oxygen, just calculate if all of the SO2 reacts, how much product do you make? If all of the oxygen reacts, how much product do you make, all right? Because the goal here is we need to figure out the limiting reactant. Why do we need to know the limiting reactant? Because that will then tell us what the excess reactant is, all right? So I'm gonna do stoichiometry twice. So I'm going to pretend, okay, all of that SO2 is gonna react. How much product do I make? So we need to get into moles. So thankfully I give you everything. So 64 grams goes on the bottom, 1 mole of SO2. And then I want to get to the product. So 2 moles of SO2 will make 2 moles of SO3, all right? So I'm actually never going to actually use the mass of SO3, so I'm not going to use the molar mass to get to gram amounts. I just need to know how many moles of the product I make, because I'll make a comparison there. So this is 1.404 moles of SO2. Oh, crap. No, that's right. SO3 is produced. Okay, that's my product. All right? So then we're going to do the same thing with oxygen. We're going to pretend, okay, all of the oxygen reacts. How much product do I make? So we do the same thing, but this time use the molar mass of oxygen. So 32, 1 mole of oxygen. Then do the stoichiometry, 1 mole of oxygen. Gives us 2 moles of SO3. I actually have to do this math. Or do I? Yeah, I do. 100 divided by 32 times 2. Wait, hold on. These numbers are messed up. 90 divided by 64. Yeah, okay, that's right. All right, so this is equal to 6.25 moles of SO3. All right, so which one of these numbers matter to us? The first one or the second one? The first one, all right? This is our theoretical yield, theoretical, all right? This number. What does that mean? It means that SO2 is our limiting, okay? And that means O2 is our excess reactant. This number we just calculated, 6.25 moles, it means nothing. Just ignore it, just erase it out of your memory, right? So notice that I'm actually never gonna use this number again. What I'm gonna do next is calculate, because look at what this question is asking. I'm not asking you how much SO3 do you make. That would have been another question, like a theoretical yield question. That could be an exam question too. This question is asking how much of the excess reactant remains. So I'm going a step further, right? Like we can figure out, yes, this is our theoretical yield, blah, there's the answer, but it's a little bit harder to recognize how much of the excess reactant is left because we have to do one more step. All right, we just determined that if all of the SO2 reacts, that's our limiting reactant to make our to make our yield. So instead of taking all the SO2 and going to product, I'm just gonna say, oh, if all of the SO2 reacts, how much O2 do I consume? So what I'm gonna do is I'm gonna take my limiting reactant, the thing I determined was the limiting reactant, I'm gonna pretend, oh, all of that reacts. So divide by its molar mass, 1 mole. But this time, I'm gonna go and ride the bus to O2 instead. I'm not gonna go to the product, I'm gonna go to the other reactant. So the ratio here is for every 2 moles of SO2, I need 1 mole of O2, right? And then here I am going to use its molar mass. So 1 mole of O2 weighs 32 grams. So when you do that, divided by 94, divided by 2 times 32, I get 22.5 grams of O2. Is that my answer? No. That is telling me if 90 grams of SO2 reacts, I also consume 22.5 grams of O2. That's what it's saying. So to get my actual answer, it's 100 minus that number. So 100 is how much O2 we started with. And so yeah, our answer is 77.5. All right, so we did stoichiometry 3 times. The first 2 was just to figure out what was our limiting reactant because I can't just look at these numbers and guess. And then the second was to figure out how much of the other reactant I consume when the limiting reactant reacts. Yes, question? Yeah. So yeah, so the question was, couldn't we just take this number, our theoretical yield, and do this instead? Yeah, we could do that, all right? Because remember, the beauty of stoichiometry and BCA tables is everything is related by those coefficients. But here's my caveat, okay? This is why I don't take this number and convert to O2. It's because we calculated this number. What if I got that number wrong? Right? What if this number was wrong and you used a wrong number to calculate O2? So instead, I'm going to use this number because it's given to us to get to O2. But you could try it. I promise you, we could do that. If we did 1.404 moles of SO3, so we're going to O2 instead. So 2 moles of SO3, 1 mole of O2 times 1 mole 32, you should get 22.5. You will get the same number. But I just warn you, if this number is wrong, then you're screwed. So that's why I use this number. Okay, all right, so let's keep going. Why would fluorine not be diatomic? Yes, oh, sorry, I missed that question. Why would fluorine not be diatomic? So remember, this is a compound. All right, we're not talking about the fluorine that you and I interact with on the street. So this compound is actually 3 carbon atoms with fluorines attached to it this way. All right, so fluorine elemental is diatomic, you're right, but this is fluorine in a compound. All right, so actually this is the compound C3F8. So there's 8 fluorines for every 3 carbons. All right. Okay. Someone wanted 25. Okay, we'll just do all of these. All right, which are the weak electrolytes? So maybe before we do that, let's identify what our strong electrolytes are. Acids, very good. I heard strong acids. So on that same note, strong acids and strong bases. There's also one more strong electrolyte. Anything that is ionic, yes. So that actually also includes bases technically, because like NaOH is an ionic compound, but it's also a strong base, all right? So that means our weak electrolytes, right, are all of our weak acids and bases. All right, so off of this strong acids list, there are 7 you need to know. So let's just go through those. Use the periodic table to help you. The halogens accept fluorine, so it's HCl, HBr, HI, then HNO3, what else? HClO3, HClO4, and then sulfuric acid, but it's only the first hydrogen, the first proton. Those are your 7 strong acids. So if you have an acid that's not one of the 7 strong, what kind of acid is it? Weak, very good. So acetic acid, weak. Carbonic acid, weak. Cyanic acid, weak. Hydroiodic acid. No, strong, yeah, hydroiodic acid is which one? HI, yes, HI. So remember, long names are short formulas. So like hydrochloric acid is what? HCl. But chloric acid is what? HClO3, yes. So long name, short formula. That's how I remember it in my pea brain. Okay, and then finally for weak bases, the only one you need to know is ammonia for now. You'll learn a lot more in 1220. A lot more. And you'll hate it. Okay, so if you can memorize those 7 strong acids now, it will be less painful. All right, so which of the following are weak electrolytes? So no, HCl, that's strong. What is this thing? That's acetic acid, so it's weak. Ammonia, that is weak. KOH, nope, that's a strong base. So I'll point out strong bases, these are gonna be metallic hydroxides. I can't spell. Hydroxides. All right, metal hydroxides. So sodium hydroxide, potassium hydroxide, lithium hydroxide, magnesium hydroxide, all of those are strong bases. How do I know they're a base? They literally have a hydroxide in them. But do not confuse them with this, CH3OH. Is that a base? No, that is an alcohol. So this is actually a non-electrolyte, all right? Do not think that that OH means it's a base, right? That is an alcohol group, not a hydroxide. All right. Which solution is predicted to conduct the most electricity? Notice that all of them are 1 molarity, but we need to figure out how many total moles of ions are there. More ions means more conductivity. So HCl, what kind of electrolyte is that? Strong. So when you put HCl in water, an H plus pops off, a chloride pops off. So 1 molarity of HCl actually gives us 2 different ions, right? 2 ions, H plus and Cl minus because it's a strong electrolyte. But HF on the other hand, that's a weak electrolyte. So when you put HF in water, will you get 2 full ions out? You won't. You'll actually get less than 2 ions. All right. So HF is going to have a dimmer conductivity than HCl. Right. So it's going to be less than 2. Oh yeah, this guy. Yeah, that is a what kind of electrolyte? Non. So if you put 1 mole of methanol in water, it's still going to be one mole of methanol, all right? So here we're gonna have no ions because it's a non-electrolyte. All right. Finally, calcium chloride. What kind of electrolyte's that? Strong because it's ionic. So let's take it one step further. You put calcium chloride in water, how many ions do you get out? 3. You get a calcium, you get a chloride, and you get another chloride. So here you get 3 ions out. So that D is going to conduct the most electricity because there are literally 3 ions there. Okay. Non-electrolytes are molecular compounds. That is a great way to, summarize it. Molecular compounds are non-electrolytes, yes. So this methanol is an example of a molecular compound, therefore it is a non-electrolyte. Other examples, CH4, diatomic bromine, iodine, all those things, they're molecular compounds. Basically, if we could draw a Lewis structure for it, then it's going to be a non-electrolyte, unless it's a carboxylic acid. Then it's a weak acid. All right. Okay. Did anyone want us to do 26? Yes? No? Fine. Fine. All right. And then I'll move on to 31. Okay. All right. So what is the minimum volume of silver nitrate required to react with 50 mils of barium chloride? All right. Here's the trick. If you see a molarity, rewrite it into an equality that's useful to you, because I have no idea what big M means. So I'm going to rewrite this into 0.035 moles of silver nitrate is present in 1 liter of solution. That is what molarity means. Okay? If something is 5 molarity, it means you have 5 moles of that stuff in 1 liter. If something's 2 molarity, you have 2 moles of that stuff inside equals to 1 liter. So that means the concentration of barium chloride given here, there is 0.045 moles of that thing, barium chloride, in 1 liter of solution. That equality is going to be super useful when we start making fractions. Because what are we trying to calculate? We're going to start with 50 mils of barium chloride. So 50 milliliters of the barium chloride thing. I'm going to just quickly convert to liters. So 1,000 milliliters is 1 liter. All right, so I'm going to use one of these molarities. Which one am I going to use? I'm going to use the one given the substance that I'm working with. Right now, I'm working with barium chloride, so I'm going to use this second molarity. Okay, now the hard part. Where am I going to put the 0.045? On the top or the bottom? On the top. Why? Because I want to put the liter part on the bottom and put the 0.045 moles of the solute on top. Okay, so if we finished right now, we would be in the unit of moles of barium chloride. Why do we love the unit moles? Because now it allows us to use the coefficients in the balanced chemical equation. I can ride the bus now, right? Where am I going to ride the bus to? We started here. We want to go here, right? We want to go to silver nitrate because we're trying to figure out the volume of that stuff that we want. So the next step is simply stoichiometry, all right? So where am I going to put the 2? Top, very good. So 1 mole of BaCl2 is 2 moles of AgNO3. All right, not quite done. We're at moles of our reactant. If this was chapter 3, we would use molar mass to get grams, but we don't want to do that. We're in chapter 4. We want to use molarity to get volume. So this is where we're going to use that other equality, all right? So where am I going to put the 0.035, top or bottom? Bottom, very good. Why? Because right now my unit is moles of silver nitrate. So if I put the 0.035 moles of silver nitrate on the bottom, that's how I get that unit to cancel. Okay. 1 liter of solution. And then then turn that into milliliters and you're done, all right? If you try to use M1V1, M2V2 for titrations, you will be wrong, okay? In this question, if you used M1V1, M2V2, because I know a lot of students who were taught that in high school, and it makes me real mad, because M1V1 is for dilutions. Is a dilution happening here? This is a reaction. So M1V1, M2V2 is a bastardization of using it where it doesn't belong. It gives you the right answer sometimes, but in this case, if you use M1V1, you will be wrong because it ignores stoichiometry. So I promise you, if there's a titration on the exam and you use M1V1, you will be wrong because we always choose reactions that have stoichiometry that you have to apply. All right, so you have to apply this step somewhere somehow. Do not use M1V1. Promise me, you won't do it? Promise. Okay, do it this way. All right, and then there it is. See, I want you to notice we've done this a million times. We did this step, this stoichiometry step, all right? We used molar mass and then did stoichiometry. We used molarity, then used stoichiometry. Then in chapter 10, we used Pivnert and did stoichiometry. All of it is the same thing. Get to moles, use your balanced chemical equation to do stoichiometry, then convert it to something else. These are just our different tools to allow us to do that, where we can go from grams, volume, or like gas properties, and then do stoichiometry. Okay, so, great. All right, so there we go. All right, 27. Oh my gosh, okay, we got 12 minutes. Hess's law. This is just adding or flipping reactions to get a target reaction. So my strategy is focus on one substance at a time and get it in the right spot. So for me, you can focus on this WO3. So I see it's right here in the target. This is my target reaction. This is what I want to try to calculate. And then here are my given reactions. And I notice, oh, this WO3, it's in the wrong number and it's on the wrong side. So I need to flip this reaction. So I want to flip it and I want to divide it by 2. So if I do that, I have to multiply by -1/2. All right? So when we do that, how else can we, okay, so then if we do that, then how are we gonna use the second reaction? So again, focus on one thing. Here I see water. Water isn't on the correct, it is on the correct side, so I don't have to flip it, but it's in the wrong number. Okay, in the given reaction, there's 2, but in the target reactions, there's 3. So what do I need to multiply this reaction by to get 3? 3 halves, yeah. So if you try to multiply by 2, that'll give you 4 waters, that's too much. So we're gonna multiply by 3 halves. So if you rewrite these reactions, you'll see that it adds up to your target reaction, but the important thing is that you want to do this math to these delta H values and then add them up. All right, so there we go, there's 27. Okay, someone said the 25, no, we did that. Okay, 40, no, 31. Okay, so yeah, let's do 31. All right, a tin atom has 50 electrons. Electrons in the what subshell experience the highest effective nuclear charge? So here is my analogy. Okay, so tin has 50 protons in the center, all right? So plus 50, that's its nucleus, all right? So when we think about like the energy levels of tin has lots of energy levels. It has N equals 1. If you look at tin's like all the way down here. There's N equals 1 electrons, N equals 2, 3, 4, in order to get those 50 electrons that we need. So if I was talking about my like N equals 1 electrons in my tin atom, and these electrons were looking into the nucleus, what charge would those n equals 1 electrons see? The whole thing. They would see all positive 50, because if you're sitting in the first row at the concert, are any other electrons shielding you from the radiance of the nucleus? No. But what if you were sitting in the second row, looking in, right? So these are n equals 2 electrons looking in. Are these electrons shielded by anything? They are shielded by those 2 inner electrons. So these n equals 2 electrons, do they see the full 50? Nope, they only see positive, 48, all right? So with that in mind, let's look at these electrons. Here we have n equals 5 electrons, here n equals 4, here n equals 3. So with what we just did in mind, all right, electrons closest to the nucleus experience the highest effective nuclear charge. Electrons towards the outside experience the lowest. So what would be our answer here? Which electron experienced the highest effective nuclear charge? 3s. Why? Because it's sitting the closest. These electrons have the least amount of shielding, right? Because they only have 2 rows of electrons in front of them shielding them. But the n equals 5 electrons has 4 rows of electrons shielding them. Right? So when we use the trick, Z effective is group number, right? So like oxygen has a Z effective of +6. That's only true for which electrons? The outermost, the valence electrons. So when you look at tin is n equal group 4. Tin is group 4. So the electrons that have a +4 Z effective are just the valence electrons. Those are, I think it's 5s and 5p electrons. Right, that's 31. What else did people want? 31. Okay, with that in mind, let's just do this page, all right? Trends. All right, so I hate when people just like memorize things and like draw stuff on their exam at the beginning and like draw these things to like memorize how size changes or like properties change. Everything has to do with size and attraction. That's how you can determine most properties. So here, all right, choose the larger atom for the following. You're gonna look at the n value. If the n value is the same, you're going to look at Z effective, all right? Because n value, higher n means more shells, your atom's bigger. So an n equals 1 is tiny, and n equals 6 is huge, all right? If you have 2 atoms that are in the same n level, then you'll look at Z effective. So higher charges, higher effective nuclear charge of valence electrons means smaller atom, all right? So just keep those things in mind. So, and then you want to look at charges. All right, charges here. So this first one, we have F2 plus, F3 plus. Remove more electrons, your thing gets smaller. Right? Electrons dictate size. So if you just remove electrons, your thing's going to get smaller, 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 smaller. All right, this one, O2 or Na plus. Okay, this one's tricky. So here for these two, they're special. They are isoelectronic, meaning that they have the same number of electrons. Na plus has 10 electrons, O2 minus has 10 electrons. So what we're going to look at is the number of protons. Oxygen has 8 protons. Sodium has 10 protons. So which particle is larger? The one where you have 10 electrons huddled around a +8 or a +10? It's going to be the +8 because that +8 attracts less strongly than the +10, the cloud of negatively charged electrons. All right, and then finally, potassium and bromine. So notice where they are on the periodic table. They are, in fact, in the same period. They're in the same row, so they have the same N. All right, so what are we going to look at? Z effective. Potassium is +1, bromine is +7. Electrons are much more attracted to +7, so potassium is the larger one. All right. So the next question, really loosely based on the same thing. Which of the following ions possesses the larger ionization energy, right? What you need to know is that when atoms are large, it is easy to remove electrons, okay? So like if you wanted to like steal like a key from me and I kept all my keys really close to my persons, would it be hard to take a key from me? Yes. But what if I just left my keys loose all around OSU? It would be very easy to steal keys from me, right? So the idea is the smaller the atom or particle, the harder it is to take an electron from it. And that's what ionization energy is. The larger your thing, very easy to take an electron from it because it's not even going to notice. It's so far away from the nucleus, not going to notice. So really, these questions are asking, if it asks what possesses the larger ionization energy, what are you looking for? The smaller thing. That's what you're looking for. All right, so K or Br, which one has the larger ionization energy? Br, why? Because it's smaller. It's smaller because of Z effective. Calcium or calcium plus, which one's harder to remove an electron? Plus, why? Because it's smaller. Cations are always smaller. Chlorine or chlorine minus? Regular chlorine, why? Because it's smaller. All right, chlorine minus is bigger, anions always get bigger, 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 okay? Phosphorus or arsenic? Yeah, I gotta look. Which? P, yes, phosphorus, why? Because it's smaller, but why is it smaller? Because of the N value, all right? All right, okay, perfect. All right, so then, same thing here. Which of the following things has the most negative, most favorable electron affinity? Here's the hint. When your added electron is close to your nucleus, typically electron affinity is very negative, very favorable, right? So putting an electron on something that's small is typically favorable, all right? So when looking at these things, chlorine or bromine, chlorine is more favorable to add an electron because chlorine is smaller. When you add an electron to chlorine, you put it closer to its nucleus than putting it on bromine. Bromine is larger, so when you put an electron on it, it's not as close to its nucleus. Nucleus is where all the positive protons are. That's where the attractions are. So here we get more payback in terms of energy released when we put an electron on chlorine. So then, aluminum or phosphorus, which one wants an electron more? Phosphorus, why? Because it's smaller, yes. Why? Because it's of Z effective. They're both in the same row, so it's Z effective. Chlorine minus or chlorine plus? Chlorine plus, heck yeah. That guy really wants an electron because it's already positively charged. Also, because it's smaller. All right. All right, so why is bromine smaller than K? Because of Z effective. They're both in the same row. Potassium is +1, Z effective. Bromine is +7. So bromine's smaller. All right, so best of luck, everybody. We'll end there.